Okay, so looking at this, what would you guys suggest that I do next?
Multiply the r's together so you get x to the r. Or the x power.
Yeah, the powers of x, when you multiply these powers of x together, you actually add the exponents. So this first term really has x to the r. And so does this one. And this one, and this one. So let's just factor it out and cancel it. Can I do it just quickly like that? Yeah, let's just do that. So we'll just cancel it out of everything. So we're not going to see x to the r anywhere. We're just going to see what we're left with after we factor all the x's out. Remember guys, exponents add here. So 3 plus r minus 3 is r. So this is x to the r here. These two things together make up x to the r. Right? Okay, so we have r minus 1, r minus 2, plus, in the second term we have r minus 1, and then in the third term we have minus 2r, and the last term we have plus 2. Okay, so that's what it's going to be. What we need to do is simplify this thing. This is not particularly nice because it's going to be a cubic equation, and I don't see immediately how to factor it yet. So let's just go ahead and multiply it all the way out. So we have r times r times r. That's going to be my r cubed, right? And then in terms of the r squared, notice that, okay, if I forget this first r and I just look at the cross term here is going to be minus 3r. So once I put the r back in there, it's minus 3r squared. And then here I have 1 times 2, that's 2, but with an r on it, so it's 2r. Then the next term is going to be plus r squared minus r, and then minus 2r, and then plus 2 equals 0. I'm just simplifying. It's just algebra right now. So I'm going to have r cubed, and then how many r squareds am I going to have?
Minus 2r squared.
Good, minus 2r squared. All right, what about the r's?
Minus r.
Yeah, minus r, because the 2 r's cancel. And then the constant term?
Plus 2.
Plus 2 equals 0. Okay. So that's what we have. Anybody got a suggestion how we could solve that for r?
Start plugging in like 1.
So you could guess a solution, you know, hope that it's reasonable. Probably on the test it's going to be reasonable. If you plug in 1 for r, you see 1 minus 2 minus 1 plus 2, that does add up to 0. So 1 is a root of this cubic equation, which just means that you could factor it out. Well, you could basically, like you said, you just basically do long division. Right? So you can just do long division, and whatever the quotient is up here is going to be a quadratic, which will be something we can then further factor, right? So at this point, we have r dividing into r cubed. That goes r squared times. Leaves me with r cubed minus r squared. And then we subtract, and we get minus r squared minus r plus 2. And then what else, what would I put next on top to match up with this remainder that I have down here?
2r
Minus r, because I need to have minus r squared, right? So I have minus r squared, and then this is plus r. So everybody see that? Minus r squared plus r. When I subtract that from what I have here, I'll be left with minus 2r plus 2, and I don't have a lot of room, is why I'm not showing my work very well. Okay, so you end up with minus 2r plus 2, and how many times does r minus 1 go into that?
2.
Negative 2 times, exactly. Okay, good. So what this tells me then is that r cubed minus 3r squared, r cubed minus 2r squared minus r plus 2 is equal to r minus 1 times r squared minus r minus 2. Okay, does that make sense? And now the r squared minus r minus 2 is going to factor, I think. Hope. How's that going to factor? R minus 2 and r plus 1. Exactly. So my roots are, how do I make each of these 0? Well, either r is 1, or 2, or negative 1. Okay? Okay with that? You know, just to point, I want to point one other thing out, if I could. Going back to just this original cubic, if you were looking for the roots, let's say that you didn't get lucky or you didn't see the roots right away. Another thing that you could have done right here, going back to this point without doing the long division, factor by grouping is what it's called. Exactly. The first two terms both have an r squared in them, leaving me with an r here and a -2 here. Right? And then here I have minus, if I group this together as a quantity, it would be the quantity r -2. And then that equals 0. And now you can factor the r -2 out. So you would get r -2 times r squared minus 1. And the roots of that are going to be these three roots again. So you could have done it that way if you needed to. Okay. Don't get too hung up, and I don't want your studying to be dominated by worrying about factoring these equations. You've got to trust me a little bit that I'm going to give you things that are reasonable and, you know, factorable, or you can get the roots fairly easily because, I mean, occasionally I'll do, I think there was one on the, there was actually a 4th degree one. Oh, I wish I could remember where it is now. Let's see, what was that? Oh, it was, I think it was this one. Yeah, I gave you a 4th degree equation. I think this was what it was. It was in the group work. And this one you had to realize, oh, if I just think of this thing as r squared instead of r as my variable, then I can factor it like that. So, you know, this is kind of the level of things that you might be asked to factor. Okay? So, anyway, but mostly we're dealing with things that are, you know, quadratics or maybe a simple cubic. Right? There was one on another group work where we had r cubed plus 3r squared plus 3r plus 1. I think that was just last week. And that one turns out it's just r plus 1 cubed. But again, you might not have known that right away, but if you try -1 for r, you quickly get 0, so you know that you can again do the long division to find the other two roots. Okay? So, but I'm not the type of guy to get hung up on like the high school algebra aspects of it so much. I'd rather see you doing the serious stuff that we're learning this semester. So once I have these three roots, then I can actually write down, we're supposed to find 3 linearly independent solutions. So what would be the solutions? That we would have, I'm going to call them y1, y2, and y3. What would be those solutions?
C1, D,
I don't want the general solution. I want the 3 individual solutions. So no constants yet. No C1s yet. Okay, right. There's no exponentials here because we remember the form of the solution. I just erased it. The form of the solutions that we were looking for were of this form, right? So we just take the values of r that we found there, which are 1 and 2 and -1, and we make these 3 solutions out of it. Make sense? So these would be the 3 solutions, and then, Erwin, if I wanted the general solution, and if this is like a complementary function to something, then I would write down C1 times the first one, plus C2 times the second one, plus C3 times the third one. That would be like the general, so this right here would be the general solution to the differential equation. Okay, so these 3 are going to be this, are going to span the general solution. Yeah, that's it.
What would happen if we have a repeated r in this one?
Then you'd have a problem. You'd have to have somebody tell you how to handle that. So it wouldn't happen. Without help, it wouldn't be able to be something I would give you. Turns out that what you have to do in that case, I'll just tell you because I know a little bit about these differential equations. If you had a repeated root for one of these kind of things, you'd have to create a second solution of the form x to the r ln of x, as it turns out, is the trick. So in the case of the problems that we spent most of our time on, if we had a repeated root, so let's say we had e to the rx, if we repeated that root r, then the second solution would be x e to the rx, right? That's how you do the repeated roots. Well, for this kind of an equation, it would be this process, but we never covered this in class. I wouldn't be expecting anybody to know that. So I'd have to tell you that, if that were the case. Okay, linear independence, let's suppose I ask you to actually verify that these are linearly independent. How are you going to do that? Exactly, we're going to use the Wronskian. So let me just show you the math of that real quick. The Wronskian is the test for linear independence of functions. So we're going to use the Wronskian. And remember, guys, we have two different Wronskians, don't we? We have the Wronskian in chapter 6, which is the one we're going to use right now. And then there's a Wronskian in chapter 7 for the vector functions as well. So you want to know them both. Basically, it's a determinant. And because this is a set of 3 functions, we're going to make a 3 by 3 matrix. Can you guys remind me, how do I build the matrix? Good, so you just put your original functions on the first row, and then what do you do?
Derive.
Take derivatives. How long do I keep taking derivatives?
You get a square matrix.
Until it's a square matrix. That's the easy way to remember it. Okay? So you just keep taking derivatives, and the third column's a little annoying because you have fractions, but it's not too bad. So we just have to take this determinant, and how would you like me to evaluate that determinant? Okay, we can do cofactor expansion. You know, the other thing you could do is you could just plug in a value for x and try to get a non-zero answer. But I'm okay with just calculating the cofactor expansion. So let's use the first column. So the first entry is x, and that gets multiplied by the 2 by 2 submatrix here, right? So that I have to do that determinant, which is going to be 4 over x squared plus 2 over x squared. AD minus BC, right? Okay. And then I have minus, remember the determinant alternates signs as you go up and down the columns. So minus 1 times the determinant of the 2 by 2 matrix that you get by the 4 numbers I didn't cross out yet. And that's going to be, well, let's see, 2 over x minus 2 over x, I guess, right? That part's actually 0. All right, so when you simplify this, it comes out to 6 over x, I think. And that is not 0 for x, any positive value of x that we might consider. So you only have to find one value of x that makes it non-zero before, and then you can say that they are Li. Okay? Everybody kind of understand how that works with the Wronskian and everything to check for linear independence? Good? Okay. All right. So we good on this problem? Yeah.
So you would just go to that step and say, therefore, since the determinant of the Wronskian is not equal to 0, get it Li.
Yeah, maybe I should write that down on the board. Okay, so I should write that down. Since the Wronskian is not 0, these 3 functions, x, x squared, and 1 over x, are linearly independent. Yeah, exactly. Please don't say something like, oh, they're linearly independent because they're not multiples of each other. That's not a strong enough reason. If I only have 2 vectors, then you can just say that they're not multiples of each other. But if it's 3 or more vectors, then just referring to one thing being a multiple of another is really not convincing yet. It's not going to be convincing. Okay, so, all right. Good on that? Are we okay with that one? Okay, let's go to another example, number 2 here. I have about 8 problems total. So, try to get you out of here by 6. I don't want you to miss the action tonight. So I'm going to take a linear operator again. I'm going to stick with chapter 6 for a little while. L is negative d squared plus 2d minus 1. And I'm going to show that x e to the x belongs to the kernel of L. Belongs to the kernel of L. Okay, so here's my main question, is how do you do this? Just like what's the approach you have to use? you want to show something's in the kernel of a transformation, what does it require you to do?
Y equals
You have to take this thing here and see if it gets killed by L. Remember, the kernel is the inputs that get killed. So what you want to do is you want to do negative d squared plus 2d minus 1. So I'm now doing the solution here. And you want to apply it to x e to the x. And you want to see, do you get 0? Okay? So let's just go through this real quickly. Notice I have minus 2 derivatives of x e to the x. So I'll just write that as minus. I'm not going to take the derivative quite yet. I'm just going to write it as minus the second derivative of x e to the x. Plus, the next term is 2 times the derivative of x e to the x. So plus 2 times the first derivative, and then minus x e to the x. Okay, so we just have to calculate these derivatives, and we should be in good shape. It might not be a bad idea to do it up here on scratch. Okay, so if I take the derivative of x e to the x, of course you're going to have to use the product rule. Right? The product rule, so it would be like the first term times the derivative of the second term plus the second term times the derivative of the first term. So you're just going to get that right there. And then if I want to differentiate that, well, the derivative of x e to the x, again, is the same thing. So x e to the x plus another e to the x, but then the derivative of the e to the x part is e to the x, so I actually have 2 of those by the time you're done taking the derivative. So that's the second derivative. I'm doing the derivatives pretty quickly. These are easy to do anyway. Just have to use the product rule a couple of times. Okay, so now let's plug all that in to see what happens. So I have negative, here's my negative, the second derivative of x e to the x, which is x e to the x plus 2 e to the x, plus 2 times the first derivative, which we already wrote down as well, okay, and then minus x e to the x. Okay. And all you really have to do is stare at that for a moment and make sure that you are convinced that it all cancels out. It should all cancel out, right? So minus x e to the x plus 2x e to the x minus x e to the x. That part cancels. And the 2e to the x and the 2e to the x, they have opposite signs because there's a minus here. So this is all just 0. That's all you have to do. All you have to do. Okay. So that's just the kernel of the transformation. Just thought I would practice that with you really quick. Okay? All right. So far, so good? Okay. Hanging in there? All right. Let's go, let's do some chapter 7 stuff. Practice chapter 7 a little bit. See if we can get anywhere with some of these linear systems. Okay. So let's practice this example here. So the third one. So let's find the general solution to x prime equals ax, where capital A is the matrix -1, -4, -2, -4, -5, -6, and 4, 8, 7. And the thing that is a little bit scary about this is there's no zeros in that matrix at all. So you want to find the eigenvalues here. You'd be subtracting lambda off the main diagonal, but you're not going to have a good column or row to expand on. If there is a good column or row to expand on, meaning that there's a lot of zeros in that row or column, be sure you know how to do it correctly, because that probably won't help you. But what I would do if this was on the test is I would tell you what the lambdas are. Because it'd be like, this is a nightmare to actually find the lambdas. So I would just tell you that, and in fact I did that on this problem on the review sheet. So as a hint, lambda is -1 and 1 plus or minus 2i. Those are your eigenvalues. Okay, -1 and then 1 plus or minus 2i. Okay, so very possible that if I'm giving you a sufficiently messy matrix, I'll probably just tell you what the eigenvalues are. So. You don't have all the lights on in here, do you? Huh? Is that better? That around that, I guess. Might be better for the video. Okay. So far so good? I don't know if you've really done anything yet. Alright, so let's take these eigenvalues in turn. Which eigenvalues would you like me to start with?
Complex one.
You want to do the complex one first? Okay, it doesn't matter. You have to do them all.
Yeah.
By the way, is this matrix defective or not defective?
Non-defective.
How do you know for sure that it's non-defective right away?
Unique height.
No repeated eigenvalues, right? So there's no repeated eigenvalues, so it's a non-defective matrix. So we're not going to be using those W's that we learned about on Wednesday. If there was a repeated eigenvalue, does that mean the matrix is defective? Not at all, right? If there is a repeated eigenvalue, it still might be non-defective as long as that eigenvalue pulls its weight, which you have to check. Okay? But here we know that since none of these eigenvalues have a weight more than 1, there's no repeats, it's definitely non-defective. Okay. This is a good thing to make sure you know, because not just for chapter 7, but even just for chapter 5, I give you a matrix and they say, is it defective or not? Well, if the eigenvalues are all distinct, then you want to know that it's non-defective. Okay, great. So let's go ahead and Erwin wants to do the complex eigenvalues first. So which eigenvalue would you like me to look at?
1 plus 2i.
1 plus 2i. Good. Okay. By the way, am I going to ever have to actually look at 1 minus 2i?
No.
No, because remember, when you think of the eigenvalues in pairs, they're going to actually produce pairs of solutions for you. So you're going to get 2 solutions out of this 1 lambda, but you're really getting it out of both of them, but you just don't have to worry about the negative one, the conjugate of this. Okay, so we're going to have to find eigenvectors that go with that eigenvalue. So I'm going to take the null space of the matrix that I get by subtracting 1 plus 2i from the main diagonal. So this is going to look a little bit rough at first. -2 minus 2i, -4, -2, and then -4, and then what is it going to be? -6 minus 2i, and then -6, and then the last row is 4, 8, and if I take 7 and I subtract 1 plus 2i from it, should be 6 minus 2i. There we go. So you just have to do that very carefully. It should be good to go. Okay. Now, what do you know? Okay, this looks pretty awful, but I'm going to show you it gets a lot better in a hurry here. So, what do you know about that matrix? Yeah, there's factors of 2 that we could take out, and maybe I'll do that in a second.
Cross out 1 row.
You get to cross out a row. That's the important thing. And that's because this matrix is definitely not invertible. If I were to do EROs to it, which right now looks like it would be a horrible job, but if I row reduce this thing, I know that at the end of the day, I'm going to have a row of zeros at the bottom. So I can cross off a row. Now we have to be a little bit careful. We don't want to cross off, we have to be sure that what we're crossing off is a row that is what am I trying to say? So like if there's only 2 rows, then the 2 rows are kind of multiples of each other. You just cross off one of them and you still have the same information. I don't want to lose any information when I cross off a row. So for a matrix that's this big, I have to be a little bit careful about that. But I know that there's really only 2 rows worth of information in those 3 rows. I know at the end of the day, I'm only gonna have 2 rows left that are not all 0. And I can just look at this and tell that the second and third row have good information in them. And that they are not, do you see that the second and third rows are not multiples of each other? Because they're not multiples of each other, I know that they will not cancel each other out somehow, right? So I don't have to worry about losing information. What I'm trying to say is I can actually cross off the first row. I can actually cross off the first row. The reason is, between the second and third row, and I'll tell you why I want to cross off the first row in a second. What I'm trying to get you to see, though, is that if I did EROs just on rows 2 and 3, I would end up getting 2 pivots. You can see that. That's because they're not multiples of each other. If the second and third row are multiples of each other, say 1, 1, 1 and 2, 2, 2, well then yeah, you'd lose the 2, 2, 2 row, and you'd only have 1 pivot in the 1, 1, 1 row. But here, I can see that the second and third rows are not multiples of each other. So I'm going to have 2 rows that survive the ERO process. I know 3 rows would never survive the ERO process. You have to have a row of zeros come out eventually. So let's just take off the first row. The reason I wanted to do that is because I like rows 2 and 3. Because I can use the addition property. Look at this first entry, -4 and 4. If I add those 2 rows together, there's no complex numbers in this first column. I'm going to get a 0 to come out of it, right? So I'm going to cross off the first row, and then I'm not done yet, so I'm going to write null space of. So I'm going to cross off the first row, and then what I'm going to do is I'm going to basically put the first row at the bottom of the matrix. That's what that means. And then I'm going to just simply put the -4, -6 minus 2i, -6 right there. And then I'm going to add these 2 rows together to write down the middle row. So -4 plus 4 is 0. -6 minus 2i, when I add 8 to that, I get 2 minus 2i. And -6, when I add it to 6 minus 2i, is minus 2i. There we go. And it's exactly what I was expecting. I got my pivots exactly as I was foreshadowing how they would turn out in those first 2 columns. I am going to take Bastian up on his idea. I'm going to divide everything through by 2 now. There's factors of 2 everywhere. Let's not carry them around with us forever. So I'm going to divide through by 2. So I'm going to divide everything through by 2. So we're going to, in fact, the other thing I might do on the first row is take out all the minus signs also. So I'm going to actually take out a -2. So this one's going to be 3 plus I, and this one is going to be 3. And then on the second row, 0, 1 minus I, and minus I. So I'm just dividing through by 2 on the second row. Okay, that looks pretty good. I'm just trying to find a vector here that is in this null space. And I know that I'm going to have one because I do have a free variable here. I'm wondering if we could try and write one down. Try to write down a vector that would be killed by this matrix. If we ignore the first row for a second and we just look at the second row, what we have is really 2 entries, which are corresponding to the y and z variables, the second and third vectors here. Do you guys remember the little trick? If I only have 2 entries and I want to kill those 2 entries, say A, B, how can we do that again?
B over E, not negative A.
Right, you